Let's have a look at our homework last night, guys. It was worksheet number 26, only 3 questions on it, all on atomic transitions. Have a look and let me know if you need any of those gone over, okay? All right, if there's no trouble with that, then we're going to go into taking a look at a multiple choice question that's related to this. We've got an electron level diagram here for Mercury. It's not quite as detailed as the one that I showed you yesterday in our example and the one that you saw in your homework questions. But in the end, it shows the same basic thing, right? And that is the energy levels, in this case in electron volts, of these different levels here. We're not calling them level 1, level 2, level 3, level 4. It's called W, X, Y, Z, and so on. Okay, not a big deal. It's not drawn to scale, so we don't see the lines drawn at varying intervals, depending upon what the energy difference is. But again, that's not a huge deal either, okay? We would like that. We would like to see the diagram drawn to scale, but in the end, what's really important are these numbers right here. Let's see what you can do over the next 60 seconds, please, with multiple choice number 173. Okay, what's the answer to the question? A. Let's take a look here. It says, what frequency of EMR is required to excite Mercury from energy level W to energy level Z? So we're going from W to Z. We're going up this way. We know that EMR has to be absorbed because we're going from an energy level that's minus 10.4 to an energy level that's minus 1.6. We're trying to go towards ionizing it, right? We're trying to go towards the infinite level where the energy is 0. So we have to absorb energy, and that's going to normally be in the form of a photon. Now, the first thing that we're going to do is find the energy of that photon that needs to be absorbed. And the energy of that photon is simply going to come from the energy difference of these two levels. So we're going to say the energy final minus the energy initial, which is going to be negative 1.6 electron volts, subtract negative 10.4 electron volts. And what do we get for the energy difference between those two levels, W and Z? 8.8? 8.8 electron volts. So that's the energy of the transition. That's also the energy of the photon that needs to be absorbed. If we went from Z to W, a photon would be emitted, and the energy of the photon emitted would be 8.8 electron volts. All right, got to find the frequency. So the frequency is going to be found by the equation E is equal to H times F. Now we get two values of Planck's constant H. Which value we're going to use, the 6.63 value or the 4.14 value? We're going to use the 4.14 value. The alternative, if you're one of those people that always like to be in joules here because you're not sure when you can use joules and when you can use electron volts, the alternative is to convert this to joules. Okay, you can do that. It's extra work, but you can do that and then use the 6.63 value for Planck's constant. It doesn't really matter. It just is a tiny bit extra work in this case. So we're gonna go with the electron volt value because that is a little bit quicker. 8.8 divided by 4.14 times 10 to the minus 15. And what does that give me? What was it again? 2.125 times 10 to the 15 hertz. So the answer clearly would be A. Now, a lot of times we look at a question like this and we can look at our options, our 4 options, and we can eliminate 1 or 2 of them right away, right? Maybe we get, something times 10 to the minus 7. Okay, well, you're not going to get a frequency that's 10 to the minus 7. Doesn't make any sense. All these are 10 to the 15. They're all reasonable numbers. Okay, they're all good numbers. So unfortunately, there's nothing that tells us when we get this number that, yeah, I'm probably right. Okay, because they're all, I would have said that for all of them. What type of EMR is this, by the way? You weren't asked that, but what if you were? What kind of EMR is it? It's going to be ultraviolet, right? Because visible light is up to 7.5 times 10 to the 14. Ultraviolet is going to be past that. All right? Good? Perfect example of the question that you might see in something like this, okay? Not hydrogen, okay? Not the numbers that we used in the examples that we did yesterday, not the examples that you did for your homework last night, but still the same process that we go through. All right. Today we're going to spend a couple of minutes talking about the last model of the atom that we look at. That's the Schrödinger or the quantum mechanical or the electron cloud model of the atom. All these different names to describe the same thing. Once we're done that, we're going to talk about some what I call subatomic particles, and then that's it. We've gone through a few models of the atom to this point, right? The Dalton solid sphere model of the atom. The atom exists as a solid sphere. There's nothing smaller. The 8-ball is different than the cue ball. Okay, but in the end, you can't break down the 8-ball or the cue ball into something smaller. The carbon atom is different than the nitrogen atom, but you're not going to break down carbon or bring nitrogen into something smaller. The solid sphere model of the atom. Then we had the Thomson model of the atom, which was the chocolate chip cookie dough model of the atom, or the plum pudding model of the atom, or as I called it sometimes, the harbor model of the atom, with the sailboats floating around in the sea. Okay, the electrons floating around in a sea of positive charge. Okay, the Thomson or the plum pudding model of the atom. Then we had the Rutherford model of the atom, which said the atom exists as mostly empty space with a small, dense, positive nucleus and electrons surrounding it, orbiting around it. Then we had what we talked about over the last couple of days, the Bohr model of the atom, which looked an awful lot like the Rutherford model of the atom, except it introduced the idea of energy levels. Electrons are in a specific spot orbiting around the nucleus, a specific level characterized by a certain amount of energy orbiting around the nucleus. And finally, we have the currently accepted model of the atom that was devised by Erwin Schrödinger in, I believe it was around 1925, 1930. Still, I mean, that's 80 years, right? Okay, we're talking about 70, 80, 85 years, whatever, something like that. It's a pretty old model of the atom, but it stands today. Okay, we still think that it's correct today. The electron cloud model of the atom is kind of like the Bohr model of the atom, but it's kind of, in a sense, a step back as well. It's kind of, in a sense, an admission of defeat, in the sense that the electron cloud model, the Bohr model of the atom was so certain with things. This is exactly where the electrons were. We had the Rutherford model of the atom, the planetary model of the atom that said, look, the electrons just orbit around the nucleus anywhere they want. The Bohr model of the atom said, no, this is where they are. The electron is exactly here. Okay, the electron has exactly this much energy as it orbits around the nucleus. When we go to the Schrödinger or the electron cloud model of the atom, it says basically that not only do we not know exactly where the electrons are, but we can't know exactly where the electrons are. There's no way to possibly know exactly where the electrons are because the electron is a wave, and there's a wave function that's associated with these orbiting electrons. It doesn't have an exact position. But when we look for it, of course, the wave function collapses. We can make predictions as to where we're going to find it, but those predictions as to where we're going to find it are purely based on probability. We could find that electron that's orbiting around the nucleus as a wave anywhere, but we're going to make a prediction based on probability where we're going to find it. It's kind of like this. Okay, if I said to you right now, where is Mrs. Ostapchuk? Okay, what do you think the answer to that question is? Okay, in the school? Okay. Probably in her office. Okay. She teaches a Religion 35 class. Maybe she's in a classroom right now. I don't know when she what time of the day she teaches it. Okay. We'll take Tristan's answer there for a second. Okay. Tristan said in the school. Okay. We don't know for sure she's in the school. You saw this morning when? When? Okay, so 15 minutes ago you knew she was in the school, right? Right now you don't know she's in the school. Now, there's a very good probability that she's in the school, right? Probably a 95% or higher probability that she's in the school. But we don't know that for sure. Okay? If we don't know where she is. If we went looking for her, there's probably a 95% probability that we would find her in the school. Now, there is a certain probability, it's smaller, but there is a real probability that we'll find her outside in the parking lot for whatever reason, maybe looking at a car that's parked in the wrong place or whatever the case may be. Okay? It's still a real possibility that she's out there. It's a significantly lower probability, but there's a real possibility that she's out there. There is a real possibility that she forgot something at home and is at home right now. Okay? It's an even smaller possibility than her being at the parking lot. There is a real possibility Okay, that 15 minutes ago, as Tristan saw her, she was on her way out the building, and now she's halfway between here and Calgary because she decided to, I don't know, go get coffee in Calgary or something. I don't know. It's an incredibly low possibility, but she could have hopped on an airplane over at the airport, across the field over there. She could be halfway to Red Deer by now. Okay, it's an incredibly low possibility that that would be the case, but it is a real possibility. The atom exists as a positively charged nucleus, mostly empty space, a positively charged nucleus. The electrons orbit around that nucleus. We don't know exactly where the electrons are. They're somewhere orbiting around it, within a cloud. We can predict where we're going to find that electron. The most probable location that we're going to find that electron is exactly where Bohr suggested that it would be. But it's not 100%. Just like the most probable location that we'll find Mr. Stafachuk is in the school. But it's not 100%. There is a smaller possibility, okay, but still a real probability that we're going to find the electron over here. There's an even smaller probability that we're going to find the electron even further out. There's an even smaller probability that if the nucleus is right here, that we're going to find the electron in High River. That's an incredibly small probability, but it's a real possibility. Does that make sense? So, as I said before when we started this, it's kind of an admission of defeat, but yet we know more. It's by knowing more, we realize kind of in a sense that we know less. It's not that we just don't, hey, look, we don't know where these things are, okay? Like, we'll do some experiments and we'll try to figure out, better where these things are. We know enough now to know that we can't know where it is. Okay, we can't know where it is. We can make predictions on probability, but that's the best we can do. Just like radioactivity, right? They're both quantum processes. Okay, just like radioactivity. Okay, we can make predictions based on statistics, but that's the best we can do. That's not only the best that Physics 30 can do, that's the best that anybody in the world can do, because it's a statistical process, right? That's the last model of the atom. What do you see up here right now? Yeah, you see condensation trails from airplanes, it looks like, right? Contrails, sometimes we call them, from airplanes. Okay, tell me what you know about this. Tell me what you know based on this picture that you see up on the board right now. Yep. Okay, so there's two airplanes, two things or two planes, okay? Good. First of all, you told me that it was condensation trails of airplanes, right? So there's airplanes, there's two of them. Okay, what else, Paige? Okay, so which one has traveled earlier than the other? Okay, so this one? This one? Okay, so this one was further back in the past than this one. Okay, I'm not going to write down all these little notes. We'll just kind of do it verbally here. So we know that there was two airplanes. We know that that this one was further in the past than this one. Okay, what else? You got to be able to tell me something else about this. Yep. I'm sorry? They're in air. Yeah, that's why we get the condensation there. Okay, what else? Different directions. They're not parallel to each other, right? In fact, they're almost perpendicular to each other. Did they hit each other? Did they collide? No, if they had collided, you would have seen a whole lot more mess in here than what you're seeing there, right? Okay, two airplanes. One was further back in the past than the other one. They're at almost 90 degrees to each other. They didn't collide with each other. This one looks like it has, to me, can't really tell on this one, but this one looks like it has two engines, right? Because you see two contrails there. Can't really tell on that newer one. I think I would say that this one is moving in this direction. Would you agree with that? Because it spreads out, right, as further back. I think this one would probably be moving in this direction, although that's kind of hard to tell, right, with that one. But it looks like it's probably moving that direction. What's the point I'm trying to make with this? Okay, you just told me, based on indirect observations, you've never seen these two airplanes. Yet you just told me a whole lot about these airplanes. You told me that there was two of them. Okay, you told me that they were going at almost 90 degrees to each other. You told me that one was further back in the past than the other. You told me that one of them had two engines. You told me that they were both going, one of them was going in this direction, one of them was going in this direction. You told me a whole lot about these airplanes without having ever been told that they were airplanes. Okay, you guys came up with all of that, including the fact that there was airplanes here. We can't see these airplanes any more than we can see subatomic particles. If we want to see some of the properties, if we want to determine some of the properties of subatomic particles, we have to have some indirect way of observing them, because we can't observe them directly. I've told you guys up until this point, well, in fact, you've been told by everybody in your scientific career up until literally the last day of new stuff in Physics 30 that the atom consists of protons, neutrons, and electrons. That's true. But those are our fundamental particles. Well, today, on the last day of new stuff in Physics 30, I'm going to tell you that we lied to you. Electrons, we still believe to be fundamental particles, but protons and neutrons, we don't. Protons and neutrons we consider, we believe have smaller particles within them, particles that make up protons and neutrons. Well, how do we know that? Because we can't see what's inside them. It's much too small. Well, we use what's called a particle accelerator. We accelerate these particles like protons to incredibly high speeds, incredibly high energies. And then we smash them into each other. It's the ultimate Guy machine. The Large Hadron Collider in Switzerland and France, it's something like, I think it's 30 kilometers in circumference, something like that. It's massive. You accelerate these particles like protons to something like 99.99% the speed of light. It is absolutely massive. It is the world's biggest machine and the world's most expensive machine. They spent something like $15 billion on this thing. Why? So we could smash two protons into each other. Tell me that's not the ultimate man's machine. Look, we want to see what's inside these protons. What are we going to do? Hey, let's spend $15 billion and crash them into each other. Why do we need such high energies? Why do these things need to be moving so fast? Well, when a car hits another car in a parking lot moving at 7 kilometers per hour, you might put a little dent in each of those cars, but you're not going to find out what's inside those cars. If two cars collide on the highway moving at 110 kilometers per hour, then they disintegrate. We find out what's inside. We overcome the forces that keep the cars together. If we want to see what's inside the proton, we're going to smash two protons together, then we need to overcome the forces that keep them together. Okay, we need to overcome the nuclear forces that keep them together. Once we get pieces out of it, once the two cars smash into each other and the pieces fly off, okay, once the protons smash into each other and the little chunks of the protons fly off, we have to observe them somehow. It's easy with the cars. We can see them with our eyes. Okay? Although when a police officer is reconstructing an accident, he or she can't see exactly what happened in the accident, right? They have to use indirect observations to determine exactly what happened. Okay? We have to use indirect observations to determine what happens with these particles that are produced by breaking up protons as well. These subatomic particles. Now, there's a couple of old-fashioned ways that we can do this. One's called the cloud chamber. In a cloud chamber, we collide these particles, the little subatomic particles, these pieces that are produced by colliding the particles, fly off into this cloud chamber, which consists of this air that has no impurities like dust, but it's super saturated with either water or alcohol. In other words, it's ready to rain water or alcohol. It's incredible. You walk in there, it's like, oh my goodness, the humidity of water or alcohol. Now, these charged particles that ionize the molecules of water or alcohol, these charged particles are the particles that came from breaking up the protons. We smash the protons together, okay, little charged particles come out of those protons. It's like bolts and fenders that fly off of the cars when you collide them, right? It's the charged particles that come out of these protons. Well, those charged particles ionize the molecules of water or alcohol. Those ionized molecules, it's not the charged particles that come from the broke up protons, but rather it's the ionized molecules that are causing this vapor. And remember, that's what it is. Okay, it's a vapor. It's air that's supersaturated with water or alcohol. It causes it to condense. So in other words, what do we get? We get a contrail, a condensation trail, just like we get when the airplanes are flying in the sky. We can tell what happened to the airplanes, some of the properties of the airplanes, simply by observing the condensation trail. We can observe some of the properties of these charged particles by observing the condensation trail. Not the condensation trail that was produced by the charged particles, but that was produced by the ionized molecules that were produced by the charged particles. So it's not only an indirect method, it's kind of a two-step removed indirect method. But it works very well. Now, there's another way to do it that's kind of the opposite. We have a gas that's been liquefied. So I guess you'd call that a liquid. But it's liquefied because it's at a low pressure. That's going to lower the boiling point just above the temperature of the liquid. So if the temperature of the liquid is X, the boiling point of that liquid is going to be X plus the tiniest little bit. The boiling point is just above the temperature that this liquefied gas is at. There's charged particles. The charged particles come from breaking up the protons. These chunks that are coming out of the proton, the fenders and the bolts that are coming out of the car, flying off the car, right? The charged particles that are flying out when the protons are broken up. They ionize molecules, just like they did with the cloud chamber. Those ionized molecules, though, don't cause anything to condense because we already have a liquid. It's already condensed. But rather, instead of causing the vapor to condense, they cause the condensation to vaporize. It's the exact opposite. They cause the liquid to boil. Then here, up here, we're causing the gas to form a liquid. Down here, we're causing the liquid to form a gas. So what do we observe? Well, we don't observe a condensation trail. We observe a cloud trail. We observe, or sorry, a bubble trail, I should say. We observe these bubbles that follow it. It's like looking up in the sky and not seeing the clouds that form behind the airplane, not seeing the condensation trails, but seeing a bunch of little bubbles that follow it. It's like the airplane, you know, is one of those little kiddie lawnmowers that you put bubbles in and you push it behind and you see the bubbles flying out the back. We get the same effect. We see the same thing. We see some of the properties of these particles that produced this condensation trail or this bubble trail. But we see it in a different way. We see it by either observing the cloud or the bubbles that follow it. That's a picture of a cloud chamber. The condensation trails that you see here, all of these lines going in circles and straight lines and spirals and everything else, they're the clouds or the condensation trails that follow these charged particles that were produced when protons or other particles were smashed into each other. Okay? They're the wreckage of smashing these protons together at 99.99% the speed of light. So what does that tell us about these particles, these subatomic particles? Well, not a whole lot when we just look at that, right? But if we if we take a closer look and understand that, look, there was probably electric fields added to this. Okay, we probably added an electric field to this. We probably added a magnetic field to this. Then we can all of a sudden say, wait, if the charged particle deflected this way in a magnetic field, and the magnetic field is pointing into the board, then we know that charged particle is negative. All of a sudden, we know something about that charged particle, right? Okay, if there was an electric field introduced and it caused the charged particle to speed up as it was going around the circle, okay, well then depending upon which way the electric field was applied, it would either have to be a positive or a negative particle. It might have to have a charge of this value, an energy of this value, a mass of this value. So we can start determining a lot more of the properties of these particles by looking at the trail that they produce, but also introducing external factors like electric and magnetic fields and seeing how they respond to that. Okay? Because we know how things respond to these external fields. So let's introduce those fields and see how these things respond to it. So after we do all this, after we smash these protons or whatever together and see what's inside, okay, by observing them in a cloud chamber or bubble chamber, what do we actually see? What do we actually see? What's actually in there? Well, there are a whole category, a whole classification system of different particles. Okay, some of which you don't need to know. I'm going to put in green what you don't really need to know. Okay, I'm going to add it for perspective. Okay, I want to show you the whole picture because the little picture that we need to know doesn't make any sense if you don't see the big picture. You might be able to remember it, but it's not going to make any sense to you if I don't give you the big picture. So in green is going to be what you don't need to know. There's two main categories of particles. There's fermions and there's bosons. Okay. Fermions are the particles that we're going to concern ourselves with here, okay? Bosons are particles that are, they tend to be force-carrying particles, okay? Or particles that or particles that are EMR, like photons, for instance. A photon is a boson. A graviton, at least it's hypothesized the existence of a graviton, is a boson. It carries gravity, okay? It's a force-carrying particle. You guys heard of the Higgs boson? Okay, the Higgs boson is the particle that's responsible for mass. Okay, it's only been the last year or so that we've actually experimentally shown that the Higgs boson actually exists. We've been looking for it for the last 50. We finally found it last year. Okay. The fermions can be broken into two subcategories. Those two subcategories, which I'm going to put in blue because you do need to know this, are the leptons and the hadrons. Now, the leptons are not mediated by the strong nuclear force. In other words, they're not affected by the strong nuclear force. Remember that force that exists within the nucleus that keeps things together, the protons, the neutrons, that pulls the nucleus together, that tries to keep it from breaking apart? Well, these leptons aren't affected by that strong nuclear force. The hadrons are affected by that strong nuclear force. The leptons, we think, to this point, are fundamental particles. We cannot break them down any further. They're as small as they get. There are 6 examples of leptons. There is the electron. Okay, that's the most common example of a lepton. Doesn't get any smaller than an electron. Okay, you can't break an electron down. As far as we know, you can't break an electron down any further. Yep. No, I didn't say it's not affected by internal forces. I said it's not affected by the strong nuclear force. Okay? That strong nuclear force that's within the nucleus keeps the protons and the neutrons together, tries to keep something stable. Okay, the electron isn't affected by that. Okay, electrons can be affected by electrostatic forces and magnetic forces and so on, but not the strong nuclear force. Okay, that's simply how we distinguish the two types of fermions. We have to have some way of classifying them, right? And that's the way that we use to classify them. Yep. No, not yet. No, not yet. No. Yep. Yep. I think they just bounce apart. The second type of lepton that we have is an electron neutrino. Now that's not nearly as common of a term, not nearly as well known as the electron, but we've seen that before, right? A neutrino is produced during the process of beta plus decay, positron emission. Okay, we call that a neutrino, but really it's what we call an electron neutrino. We just left off the first word. The reason we're now calling it an electron neutrino instead of just a neutrino is because there's other types of neutrinos as well. The one that we saw, though, was an electron neutrino. But the good news is that's the only one that we'll ever see is the electron neutrino. The only one that we'll ever have to deal with, that is. There's also another type of lepton called a muon. And of course, goes along with a muon would be a muon neutrino. We're putting that in green because you guys don't really need to know this. But again, it's perspective. So that you understand there are other particles in the class of electrons. There's the tau. There's the tau neutrino. Plus all the antiparticles. The antimatter equivalents of the electron, the electron neutrino, the muon neutrino. The antiparticles would be the anti-electron. What's the anti-electron, by the way? Positron. The anti-electron neutrino. The antineutrino, right? That's what's produced in beta minus decay, the antineutrino, the anti-electron neutrino. There's the anti-muon. There's the anti-muon neutrino, the anti-tau, the anti-tau neutrino, although the last four we don't have to know about, right? Then we go back to the hadrons. These hadrons that are mediated by the strong nuclear force, that are affected by this force that exists within the nucleus. They are made up of, because they're not fundamental particles, they're made of quarks. Some examples of hadrons, by the way. Give me an example of something that's mediated by the strong nuclear force. Proton and neutron. There are others, but that's obviously what we would concern ourselves with, the proton and the neutron. They're made up of quarks. There's 6 types of quarks. When I graduated high school, we hypothesized there was 6 types of quarks, but we'd only ever actually found 5. We'd only actually observed 5. Okay, but it's been quite a few years now since we've observed the 6th type of quark. Okay, when you're graduating high school, we talked about those bosons, the Higgs boson. Okay, we were just at that cusp of discovering the Higgs boson. In 20 years, that's old news, right? Just like the 6 types of quarks are old news now. There is the up quark. These are great names for these quarks. The up quark. And there's the down quark. Those 2 types of quarks had both been discovered, I'm not sure when, to be honest, but certainly before I graduated from high school in 1990. So they're old. There's the top quark and the bottom quark. The top quark, whoops, we shouldn't put that in blue. Those should go in green. The top quark and the bottom quark. The top quark is the one that hadn't been observed experimentally when I graduated from high school. We knew that it should be there because of symmetry, but we hadn't actually seen the top quark. We hadn't actually observed the top quark. Stephanie, you asked a question a few minutes ago. Smash these protons together, what do you get? Okay, when we smash protons together, we get quarks. So we're observing the condensation trail or the cloud trail of quarks. Okay, up quarks, down quarks, top quarks, bottom quarks, so on. Then we have the charm quark. They seem to be getting stranger and stranger, hey? The up quark, the down quark, that's kind of okay. The top quark, the bottom quark, the charm quark, They're getting stranger and stranger. In fact, the last one is the strangest one of them all. The last one is called the strange quark. The up quark, the down quark, the top quark, the bottom quark, the charm quark, the strange quark. And what else? The antiparticles. So there's the anti-up quark, also known as the Texas Hold'em quark, the anti-up quark. There's the anti-down quark. You'd think the anti-up quark would be the down quark, right? But it isn't. Okay, that's a separate thing. There's the anti-up, and then there's the anti-down, which is different than the up, than the down and the up. There's the anti-top, which you might think would be the bottom, but it isn't. There's the bottom, and then there's the anti-bottom. And then there's the anti-charm, and then there's the anti-strange quarks. Now, there's one more little thing that we're going to add to this. We're going to put this in red, because you need to know it. You need to be able to do it, but it's on your data sheet. So you don't need to actually remember it. The charge of an up quark is 2/3 of the elementary charge. So much for the elementary charge. That's an oxymoron, right? 2/3 of the elementary charge. 2/3 of the smallest possible charge you can have. The charge of the down quark is -1/3 of the elementary charge. The symbol, by the way, for an up quark is a U. The symbol for the down quark is a lowercase d. Now, the other ones have charges as well. To be honest, I don't even remember what the charges at the top quark and the bottom quark and the charm quark and the strange quark are. Okay? If you ever saw a question involving these ones in green, they would give you whatever information you needed, and they would tell you about it. Just like they give us a page of context of, whatever, right? Okay? They could give us something that's in green here, but they would explain it if they did. Okay? Good? All right. I want to look at, just briefly here, we're almost done. I want to look at how up quarks and down quarks make up protons and neutrons. And then I want to look at how they're involved in a certain type of radioactive decay. In each particle, a proton and a neutron, there are 3 quarks. And those 3 quarks are combinations of up and down quarks. Remember, an up quark was +2/3. You don't need to remember that. It's on your data sheet. A down quark is -1/3. If a proton consists of 3 quarks, up, 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 down, 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 up, down, down, up, down, whatever, some kind of combination of 3 up and down quarks, what combination would it be? There's only one possibility. Tristan, what are you saying? Up, up, down? Let's try it. Up, up, down. An up quark has a charge of 2/3. An up quark has a charge of 2/3. A down quark has a charge of -1/3. What does that equal? 3/3, right? So, in fact, that is the composition of a proton. When we smash a proton into another proton, we get some up quarks and some down quarks. Twice as many up quarks as down quarks. What's a neutron consist of? Up, down, down, did you say? Let's try it. An up quark is 2/3. A down quark is -1/3. A down quark is -1/3. Let's add them up. What do we get? 0. Okay, that's the charge of a neutron. So a neutron consists of an up quark, a down quark, and a down quark. So much for protons and neutrons being fundamental, right? Okay, just like the atom is made up of protons, neutrons, and electrons, a proton is made up of an up quark, and a down quark. And similarly, a neutron is made up of an up, down, down. Yep.
So if you collide a proton with a proton,
yep.
How do you get another fundamental particle?
I'm not sure. I'm not sure. By simply colliding two protons, I'm not sure where that would come from. Yep. Where do the other quarks go? Well, other quarks are compose other things. So we talk about these two bosons, not bosons, but hadrons, the proton and the neutron. Okay. In this case, the proton, right? Collide two protons. We get up quarks and down quarks out of it, right? Well, the other quarks come or compose other things, compose other particles. Well, there's all kinds of other particles, right? I mean, sometimes we call it the particle zoo. Okay, there's all kinds of examples of hadrons, all kinds of examples of bosons, and these leptons, whatever. Now, what we find makes up matter, okay, what makes up matter are the electron, the proton, and the neutron. And that's why we're looking at this very narrow, I've put in blue a very narrow range of this. This table is far from complete in terms of examples of stuff, right, and descriptions of stuff. And even within this table, there's only a very narrow bit that we have to know. The whole idea of the electrons, protons, and neutrons and what composes those and so on. But there's lots of other particles. Okay, we talk about the particles, electrons, protons, and neutrons, because they're the ones that make up matter. But things like photons, examples of bosons, right? Photons. Well, we've talked a little bit about photons, okay, but they don't make up any matter, right? They're particles that don't make up matter. Gravitons, we hypothesize the existence of these gravitons that are responsible for gravity. Okay, the Higgs boson, okay, it doesn't make up matter, but it's responsible for mass. Okay, so there's all kinds of other particles that aren't matter. Okay. Yep. Oh, no, I don't believe so. I don't think any of them would. Last page. And look at that, it's a short page too, isn't it? Good one to have as a last page. What the heck is this? Beta decay up. Oh, didn't we learn beta decay is something like this? Like 14 carbon, 14.6 carbon goes to 0 minus 1 beta plus 14.7 nitrogen plus an antineutrino. Wait a second. Now we're talking about up to. This is just a description of beta decay in terms of quarks, a more fundamental description of beta decay. Up, down, down. Okay, up is what? Up is 2/3. Down is negative 1/3. Down is negative 1/3. What's the charge there? 2/3, negative 1/3, negative 1/3. 0. So what's this going to be? A neutron. All right. Well, that's what beta decay is, right? A neutron is changed into a proton and an electron. Okay, let's take a look here. Up, up, down. What's up? 2/3, 2/3, and negative 1/3. That adds up to give me 1 elementary charge, which is a proton. So now we got a neutron that's changed into a proton and an electron and an electron antineutrino, right? Now, we just call it usually an antineutrino because that's the only kind of neutrino and antineutrino that we talk about is the electron antineutrino. But strictly speaking, okay, we should probably call it the electron antineutrino because there is the muon antineutrino and so on. So look at this one. Up, up, down. What do we got there? Well, up is 2/3, 2/3, negative 1/3. Charge there is 1 elementary charge. What's that? That's a proton, right? Up, 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 down, down. That's going to be 2/3, negative 1/3, negative 1/3. That's going to give me a charge of 0, right? What's that? A neutron. Well, beta plus decay, positron emission, is when a proton decays into a neutron and a positron. I didn't tell you this when we talked about positron emission. Okay, but it's technically a two-stepper, a two-step process. When a proton decays into a neutron and a beta plus, okay, that's what this is, right? Is a positron, a beta plus particle. It actually happens in 2 steps. The proton decays into a neutron and what we call a virtual particle. And then the virtual particle decays into a positron and a neutrino. You don't really need to worry about that. Okay, if you consider it to be one step, that's fine. Okay, so a proton up, up, down decays into a neutron and a positron right here. Plus, what else? An electron neutrino, right? Again, if you call it a neutrino, that's fine. Strictly speaking, it's going to be an electron neutrino. Is that a good? Guess what? We're going to start our new unit now. That's it. That's it. That's all.